Hi and welcome to my tutorial about equalization using the WaveCapture software. I will show you an efficient way to create parametric filters with a sequence, and I will promise you that it will be much quicker than so-called silent tuning. We start with a measurement made of log sine sweep, and it's we are using multi-time windowing here to extract the direct sound. We go to the target. We don't want to have it flat. We want to have it for example, outdoor rock festival. We choose the pass band like this. So we calculate the average level in the passband. We go to the optimizer. We have chosen lake controller or lake type of rate cosine filter. It provides 27 filters as maximum. And we start the optimizer. And we see the count here. And here we have the list of raised cosine filter, like this. And then we go to the export section and save this in the lake controller folder for EQ overlays. If you want to hear about more details, please hang on. This is a trace coming from an average of 7 different measurement positions. That is for minimize the influence of reflection from the room. On the bottom here you can see the Kepstrom representation of the time domain. So this is made in a single log sine sweep. Plays 7 microphones and an 8-channel sound card, and just one sweep like this, and all 7 curves are captured in one sweep. We can look at the face. The wrapped face doesn't say so much here. We can see the group delay, and this is the remains from these peaks and notches. Is the remains from the room reverberation and reflections. We can apply a multi-time window, so we can wash out the room further. Let's go to the target. While creating parametric filters, it's important to choose a reference level, so the optimizer know where the average level is. As you can see, you can drag this, and in this case it will produce a lot of peak gain, and here a lot of notch gain parametric filters. But one way to figure out or calculate the average level is to use these cursors, and you got an RMS average level here. So just try to make this measurement flat, this system flat, just to show how the optimizer works. So we take a generic, and then we have a minimum bandwidth here, and so you can steer how much bandwidth you allow for the peaking and for the notching parametric filters, and these are also control if this filter doesn't make it. Now you see you have a quite big range for the filter here, but if we limit it will need to place maybe several filters in at the same frequency. Before we start the optimizer, we have to define in which frequency range we'll put all these 32 parametric filters. So we take these cursors and define a frequency range. We can also type it in here in numbers. And then we try the optimizer. And it becomes quite flat. And here we can see the list of all the parameters. And we can look at the filter itself. It's quite a lot of high Q, and that will not sound so good, I think. So we can go back and then we reduce or increase the bandwidth of the peaking filters. And run the optimizer again. Okay, a little bit better. And this is the total result. You can look at the group delay here. And some peaks are remaining here due to reflections and so on in the measurement. And then we can go through all the filters here. And we can edit them. We can take away this filter, for example. Here is another one. We can remove it. Or we can go back to the parameters here and say that not allow so high peaks. Now we see that there are only notching parametric filters left. Usually you don't want to have a flat response of your system. It's only for studio monitoring, etc. You want to have something like a bump in the bass and maybe a shelving filter on the high. And there are several such targets included in the software. So you can choose these text files. They are quite simple. For example, a shelving. It's just to tilt. It's just to define a frequency and a dB level in the text file. Or you can create your own by make a shelving filter, low shelving filter like this, and make a butterwort filter, for example, like this, and then you adjust the average level according to this. And then you go to the optimizer, and then all the filters for this target curve is calculated. Again, we avoid high Q peaking filters. So here we can see the result. Then you can export this in several formats, XML, or if there are, we have different hardware device which is available for the software. So you can choose a lake, for example, and then you got the settings for this with 27 parametric filter or type raised cosine filters. Okay, this is the total filter. And then you can export this as an overlay to the lake processor. In many cases, your hardware doesn't allow for thousands of parametric filters. Usually there are only 12 in your DSP in the amplifier, for example, and you want to use these filters as efficient as possible. So one way is to steer those filters in an efficient way. Let's say that we want to focus most of the filters in the vocal range. So we place 6 filters there, start the optimizer, and then we have 6 left. So we place 3 of them in the sub, and then we continue the optimizer like this. And then we place the remaining 3 parametric filter in the high frequency region. Like this, and continue optimizer. And here do we have the result of the 12 available parametric filters.